We're starting at elevation 0, 0, right? We have to get to an elevation of 14 feet. 14 feet is, in inches, is 168 inches. So we have to climb vertically 168 inches. And because it's more than 12 feet, right? 12 feet is 144 inches. It's somewhere over here. We need a landing. So we need to rest. So we're going to go from 0, 0 to a maximum of 12 feet. And then rest. And then from the difference between that elevation, which is 12 feet or less, to 14 feet. Okay? So this is flight 1, and this is flight 2. This is schematic now. I'm not drawing it in actuality. I'm not drawing it scale. To climb to 168 inches using treads and risers, stairs. Let's do a quick sketch of what a tread and a riser here. Imagine that we're looking at this in section. This is the floor. This is the height of a riser. That's 7 inches or less. The options for this problem are to use risers of either 6 inches or 7 inches. Why are we using risers that are 6 or 7 inches? That's the vertical height of the step. Because these 6 and 7 divide evenly into 168. For purposes of this problem, I chose to make the floor-to-floor height a perfect multiple of 6 or 7 inches. So if I divide 168 by 6, I get, can't do that in my head, I get 28 risers. If I divide 168 inches by 7, I get 24 risers. The riser is the vertical single increment of this stair. The horizontal increment of the stair is called a tread. The tread minimum is 11 inches. So the total number of risers is going to determine not only the vertical distance that we can climb, but the horizontal projection, finally, of the stair. So here I've drawn 1, 2, 3, 4, 5 risers. Okay? There's always one less riser than there is a tread. So this is one tread. One less tread than there are risers. This is one tread, 2 treads, 3 treads, 4 treads. And the last step is the landing. So we don't call the landing a tread because this is the stopping point of the flight, and it needs to be as deep as the stair is wide. We'll talk about that when we look at the stair in a plan drawing. So the decisions we're going to make here are three altogether. First decision we're going to make is what is the height of the riser that we're going to use? Well, I made that easy. We've given you a choice of 6 or 7. So that's a matter of your choice. Right? Under real life circumstances, the height of the riser is determined by the number of risers divided into the height that you're going to climb, and that riser cannot exceed 7 inches. It might be less than 7 inches. It could be 6 inches and a fraction of 7, but it can't be less. I should say also that when the typical tread riser combination, the preferred, is a 7-inch riser plus 11-inch tread. And usually if the riser decreases to like 6 inches, that usually implies an increase in the depth of the tread. So if I were using 6-inch risers, I'd probably make the tread at least 12 inches. So the distance the horizontal projection of the stair is going to be the number of treads that cover that distance times the depth of the tread. So if the tread is 11 inches, and here we have 4 treads, then it's going to be 44 inches. 4 treads at 11 inches equals 44 inches. If it's 4 treads at 12 inches, it's going to be 48. I hope we can see this. So you decide on the height of the riser. Then you need riser plus tread combination, which I explained here. Riser and tread. So 7 and 11 or 6 and 12. Then you need the floor to floor or flight to flight heights. Flight to flight heights. There are 2 flights here because the floor to floor height, let's call this floor 1, and let's call this floor 2, exceeds 12 feet. So we need a resting place in between. So distance to that resting place, which is going to be the form of the landing, it's called a flight. So flight 1, flight 2. In the next video, we're going to begin drawing what the stair. We're looking at basically an elevational view of what the vertical projection of this stair is going to look like, right? We're looking at a section drawing here, or an elevation depending on where you're standing. But when we look at the stair in a flat point of view, we're going to draw a plan drawing. Let's imagine that each of these treads projects downwards, and the landing projects downwards, right? And I'm going to draw a line here that represents one edge of the stair, the outside edge of the stair. Now I'm looking at plan. Here I'm standing in front of the stair. That may not be at scale. And here I'm standing in front of the stair, but you're looking down at me, at you or me, right? This distance is the width of the stair. Stair width. "44 inches is minimum in most commercial applications. 48 is preferred. We're going to use 48 to make this easy. And the landing depth must be at least the width of the stair. So if the stair width is 48 inches in this direction, then the landing depth has to be minimum 48 inches. It can be more, but it has to be at least 48 inches. So that's the section drawing, section or elevation. I'll write both because we're looking at orthographically that stair as if we were standing in front of it and perpendicular to picture plane or field of vision, right? Looking at it straight on. And in plan, the stair looks like this. It begins here and goes in that direction in this drawing, up, UP, up. I should say also, as a rule, there ought to be a space in front of the stair that's at least the width of the stair as well. So think of it as a imaginary landing space in front of the stair that is at least as wide with before stair. Before the stair begins. That's at least as wide of this as the stair. So that's going to be 48 inches. We haven't decided on number 2, or flight to flight heights. You got to choose a number of risers from that go from 00 to flight 1, that the sum of which does not exceed 12 feet or 144 inches. If you're going to make it exactly 12 feet, if we're using, let's say we use the 6-inch riser, which means we need a total of 28 of them, then that's going to be 144 divided by 6. That's going to be 24 risers. Usually we try to split them evenly if you can. It depends on the layout of the plan. But for purposes of this assignment, I'm willing to ignore that. So decide on, this is 12-inch or 12 feet or less. Decide on the elevation of flight 2. Okay. Let's, for argument's sake, cut the distance in half. Let's say flight 2 landing is at 7 feet. Flight 1, the distance to flight 1 is 7 feet. So the distance from the landing, the resting place, to the top, which is flight 2, is going to be 7 feet as well. So this is going to be 7 times 84 inches divided by 6 is going to be 14 risers. 14 risers. And then flight 2 is going to be 14 risers. 7 feet, 7 feet. So the flight to flight heights are 7 feet and 7 feet. The next decisions that we make are going to be in a plan projection, so looking down at the stair. And we have options when we do that. The stair in plan can either be what's called a straight run, right? Think of this as the horizontal projection of flight 1, then a landing, then flight 2 continues up, right? This is a straight run. The other option is for the stair to make a 90-degree turn. It can make turns at different angles, but those are going to be more complex than we want to discuss here. But let's say flight 1 goes up to a landing and then makes a 90-degree turn. The stair would look like this in plan. I'm not drawing its scale. Flight 1, landing, up, and this is flight 2. And then your destination is at the very top. Your starting point is at elevation 0, 0. When you reach this landing, you're at elevation 7 feet 0. So this is 7 feet 0. And when you reach your destination, or floor 2, you're at 14 feet 0. So let's try to get this far along in our understanding of the parameters of what we're going to draw. 25 minutes is enough for this part of the problem.